Okay, it's supposed to start recording. Okay, now we're recording. All right. Now, to those of you who are watching this who were not in class, my apologies again. I started going through the first problem until it was finally brought to my attention that I forgot to record. Again, my apologies. Please bear with me. Okay, so I started talking about this problem. We have a matrix times a vector equals another vector. This operation only makes sense if the number of elements in the vector, which is x, equals the number of columns in the matrix, which is A. The result will have the same number of rows as A. So what is the definition of this operation? So this is what I've explained here. What you do is, there's different ways of understanding how this works, but I feel like the easiest one to retain is you take each column, so that's a vector, and then you multiply it by the corresponding element of a vector. So I'm going to take the first column A, multiply it by the first element minus 3. Then I'm going to take the second column, this vector, multiply it by the second element of a vector, so 5. So this column times minus 3, this column times 5. So however many columns you have, which will match however many elements you have here, so just go across the columns from left to right, multiply them by the corresponding elements of a vector from top to bottom. And once you multiply this by this, this by this, add them up. So I will show that here. Okay, so here I have a first column times minus 3, and then I will fill in the rest. All right, so here I have 5 times the second column, and then we still have a column on the vector on the right side. Okay, so this right here is the matrix vector product. And what we have here, this is actually a vector equation, because we're saying a linear combination of these vectors equals this vector on the right-hand side. So this is how we go from the matrix equation up here to this vector equation down here. So to finish off this operation, you would go ahead and multiply these out, like you distribute the minus 3 to all this and the 5 to all this. And what you would get would actually be the elements of this vector. Now, so here we go one step further, and we have a system of equations first, and we want to get all the way to a matrix equation. Now, I'll show you this in stages, but then how to jump directly to a matrix equation. Okay. So how to get to a vector equation, that's actually something that was seen last class, that we break the left side down into vectors according to which terms have an x1, which terms have an x2, and however many unknowns you have. All right. So what happens here is for first unknown, every term involving x1, so we write those separately, and then the second vector, every term involving x2 from the left side, and then we still have the same right side. Okay, but then you take x1, factor it out of this. You take x2, factor it out of this. Okay, so I'll show you that. Okay, so first we're going to have x1 on the outside, and its elements. So the coefficients of x1 are what are left behind. And then we pull out x2, and we have its coefficients left behind. And then the same right-hand side vector. So what we have here, this is a result of a matrix vector product, where the vectors involved are the columns of a matrix. What's multiplying them, the x1 and x2, those are the vector x. So we just take whatever vectors we have from our vector equation, and we put them together. Let's go on the right side first. That part did not change at all during this whole thing. So now, for a matrix, so we just put the columns next to each other. And then what's multiplying them, so going from left to right, we fill the vector in that order. And the vector has to go on the right. So whenever you have, you can think of this vector as a matrix that only has one column. So for matrix multiplication, as I mentioned, the number of columns must equal the number of elements, number of rows of the matrix that's on the right. Now the thing is, of course, this left side, I could have written it in either. I could have written it either way, but I could have x2 times this vector plus x1 times this vector, because of a commutativity. And what would have happened in that case? I could have put this column first and this column second. But the reason why it's not a contradiction is if I did that, then x2 would go up here and x1 down here. So there we'd have a different matrix, different vector, but the product of them would be the same. So that's something that can happen. So now we've gone from this system of equations to the same system in matrix form. So so to get the matrix, all you have to do is look at the coefficients of your unknowns. So whatever's multiplying x1 is your first column, whatever's multiplying x2 is your second column, and so forth. The unknowns, x1, x2, etc., however many you have, will fill this vector in order. So then there's no need to go through, and if a problem in my labs requires this step of getting to a vector equation first and going here. But you can see just from the patterns of how it's written, how to jump from this directly to this. So if you're given a system of equations to solve and it's written like this, you're just going to jump to this for the purpose of performing row operations to actually solve a system. Okay. All right. Let's make sure there wasn't anything new in chat. Okay. So now we have more problems that are involving matrices to effectively solve systems of equations. And I mentioned the equivalence between these things last time, and I'll highlight it again here. So here we have a given vector and a given matrix. Now, when we have two vectors like this in three-dimensional space, those two vectors generally define a plane, unless they're parallel to one another, which is what happened in one of the problems I went over last time. So the question is U a linear combination of these vectors? That's another way of phrasing this question. Okay, so if U is in the span of these columns, so if it's in this plane, therefore U is a linear combination of these columns. But that's the same way of saying that this system of equations, AX equals U, has a solution. So what you're going to see in several of these problems is whatever it is that's being asked, like is U in the plane spanned by these columns, ultimately boils down to a system of equations that has to be solved. And oftentimes performing row operations, getting echelon form to determine if a system can be solved, and then if so, actually solving it. So what we're going to do is actually solve this system, and if there is a solution X, then the elements of X are the coefficients in a linear combination of these columns that will give us U. So the problem is asking, is U in the plane? Does this system have a solution at all? So that's the same as determining whether the system is consistent. So what we do is we take the columns of A, and then we add on U as an additional column. So now we have an augmented matrix. So that's how these kind of problems are going to go. Based on what the question is asking, determine what system of equations needs to be solved, and then we make the augmented matrix for that system. So here's the left side, right side. So then, once you have your augmented matrix, then you can do what has been done in many other problems, is carry out row operations. So if I want to take this matrix and reduce it to echelon form, at least, that'll tell me if it's consistent. I want to find out what do I need to multiply this row by to subtract from this row. Can anyone tell me what that would be? I want to eliminate this element right here.
Negative.
Sorry, audio cut out.
I said it's a third.
Yes, negative 5/3. Now, so we're going to subtract minus 5/3 of times row 1 from row 2. So that, in other words, row 2 is itself plus 5/3 row 1. So then we go ahead and eliminate that entry. And unfortunately, we see that the numbers are not so nice anymore. Unfortunately, that's something that can happen. So don't assume things will work out nicely. And then how do we eliminate this element? What's the row operation in that case?
That is 2/3.
Yeah, so row 3 will be itself. Okay. Oh, sorry, I scrolled to the wrong place. Minus 2/3 row 1. Okay, so taking care of everything in the first column that needs to be eliminated. And what we can see here is if you ignore all the denominators are the same, but notice that if you take this row and multiply it by -4, you're going to get this row. So that actually tells you that you see that the ratio is -4, like this row to this row. Here again, the ratio is -4. These rows are parallel. And when you have rows that are parallel, then when you perform a row operation to eliminate an element, you're actually going to wipe out the entire row. So here the ratio is -4/3. So, or sorry, the ratio is just plain -4. So row 3 is equal to itself plus 4 times the second row, and we get a row of zeros. Now this is an augmented matrix. So because that row is all zeros, and all other rows have a pivot element in them, so this system is consistent. So we can say that U is in the plane spanned by these columns. So that answers the original question. Because there's a row of zeros, let's see, but we have 2 pivot positions here, the 3 and the 1, 1 position and the -4/3 pivot position too. We have so 2 pivot positions and we also have 2 unknowns, x1 and x2. So I can make an additional comment here. Is that because the number of pivot positions equals the number of unknowns, 2, there will actually be a unique solution. So we're going to go ahead and solve the system. So now that it's row reduced, we can go ahead and solve it. So what we have here is, since it's in echelon form, this is the to solve for x2, we can just divide this by this. So what we end up with is, okay. So we just divide these to get 4 for x2, and then so then to solve for x1, we have this equation. So the equations that are being applied here, implied, so it's important to be able to see like what equation needs to be solved just from reading it off a matrix. So the second equation is the one we solve first. We're going from a bottom up. Okay, we'll put parentheses around that so there's no ambiguity. Okay, so we solve that first for x2, and then the other equation is 3x1 minus 5x2 is equal to -5. So that's actually what we're solving here. So you need to be able to read that off from the echelon form. So here we can see we can solve this just by dividing. Here, this equation needs to be rearranged to get x1, but that's what's done here. So then and also the value of x2 that's now known from here gets substituted into this equation, and then we go ahead and get the result of 5. So the unique solution is 5, 4. So what we have found I need to get to the right place here. Okay. So 5 times the first column plus 4 times the second column. And these are first and second columns of A. is equal to U, because that's how a matrix vector product works. That you take each column of A multiplied by the corresponding element of X and add them up. Some questions about this one? So any problem in which you're asked whether a certain vector is in the span of columns of a certain matrix, you're solving this system where so this matrix and then this column added on the end, that's your augmented matrix. That's what you'll be working with for performing row operations. All right. So, so the next problem is same kind of situation. We just have a matrix with 3 columns. So to determine if this vector is in the span of these columns, we work with, let me put this on a new page. Okay. Okay, so we just jump directly to the augmented matrix. So A with U added on to the end. And this is how the augmented matrix can be written, indicating where the columns come from. So matrix A and then the vector U. So like before, this is what we would perform row operations on. Now all that's going to unfold the same way as in the previous problem. So, we're not going to dwell on the row operations in this case, but rather what we see as a final result. So here we're taking the same ratio and subtracting to get the elements in the first column eliminated in row 2 and row 3. And then we go ahead and move to the second column. See that the ratio here is 3/2. So row 3 is itself minus 3/2 row 2. And once we carry out that row operation, this is a matrix that we get, and this is bad. What we have here is from the matrix, the third row of the original matrix A has been reduced to 0, but we have something non-zero over here. So when that happens, the row is all zeros except for the last element. When it's an augmented matrix, that system is inconsistent. So what we could conclude in that case is the vector U that we originally had on the right-hand side is not in the span of the columns of A. So what we can see from this example is here we have 3 vectors in 3-dimensional space. And you might think, well, if you have 3 vectors from 3-dimensional space, that those, because it's 3-dimensional, those 3 vectors should describe the entire space so that any vector can be described as a combination of them. Most of the time, that is true. But what these row operations show is that one of these vectors must be a linear combination of the other 2. So in other words, it becomes redundant. So really, these 3 vectors do not describe the entire space R3. They describe what's called a subspace of it. That would be only 2-dimensional. So these 3 vectors only describe a plane. So not all points in free space are in here. So if I had chosen a different U, so that the row operations would end up giving me a 0 over here, that system would be consistent. And actually, there would be infinitely many ways to describe that vector as a combination of the 3 that were given. All right. This next problem Similar idea, but that's a somewhat different question. Because here the matrix, sorry, the right-hand side is not specified. It's just some numbers B1, B2, B3. So we're going to work with the augmented matrix and show that it does not have a solution. So in other words, the system that we get is not necessarily going to be consistent. But then the question is asking, are there certain B's, the choices of B1, B2, B3, so that the system is consistent? So when we're talking about the system having a solution, that's the same as asking whether it's consistent. So what we need is, like before, a an echelon form. You notice in these examples, I could go to reduced echelon form, but it's really not necessary to actually solve a system or determine whether it's consistent. So here's my augmented matrix. Now, what's going to happen when I perform these row operations, like before? So row 2 will be itself plus 3 times row 1, because again, I'll take this ratio, and that's what gets subtracted. So minus a minus 3. And of course, we're performing a row operation in all columns. So this second element, B2, will be replaced with itself plus 3 times the element from the first row. So that's why we have a free B1 down here. So we're going to have a symbolic, right-hand side right here. Then we do the same with the third row. So the row 3 is equal to itself minus 2 times the first. Okay. And then we get this down here. Notice if we look at the matrix entries, these just focus on the 9s and minus 9s. So forget the right-hand side. These rows are parallel to one another. They're just negations of each other. So all we'd have to do is add these rows together, and therefore add these together also, to perform the final row operation. So row 3 is equal to itself times row 2 Okay. And sure enough, because these were parallel, row operation ends up wiping it out. So we have all zeros down here. So then we add these together also, and what do we get? We get B1 plus B2 plus B3. Now remember, from the last problem, last two problems actually, the system is consistent only if this is 0, because we have all zeros over here. We only have these two pivot positions. The third unknown, x3, would be a free variable. But if this is non-zero, then the system is not consistent. So the only time it's consistent is when whatever you have down here is 0, because there is no pivot position in the third row, only the first two rows. So what we see from this is when you have a system like this where row operations would introduce a row of almost all zeros here, except for the right-hand side, for most right-hand sides, the system would be inconsistent, because we're requiring that this be equal to 0. So if this is anything else, there's no solution at all. So here's another question about whether a system can be solved. Again, the right-hand side is not specified. So what we want to know is, does this system always have a solution or not? So how does this relate to pivot positions? So system AX equals B has a solution for any vector B, all right, and I'm going to make an assumption here where A is n times n matrix, number of rows times number of columns. So n rows, n columns. So a case of a square matrix. So it has a solution for any B in the space Rn. So in this case, n is 4. If and only if the echelon form, echelon form has a pivot position in every row. So, in other words, if I were to row reduce this and have any row that is entirely zeros, then I know that there's going to be some B out there for which this system is inconsistent, like what happened in the last problem. That it will always be possible to find such a B that ends up not working. So then you go through the process. So we don't have an augmented matrix this time because we don't have a right-hand side. So here we go ahead and perform these row operations. So in other words, for the second row, we add these two rows together. All right, and we get that. This element is already eliminated. There's only this one. So here the ratio is -3. So I'm going to add 3 times this row to this one. Okay. And that, so now the first column's taken care of, and then we keep going. So here we have a ratio of 6. So 6 is the multiplier, if you will, or what multiple of a row we subtract. And what happens when we do that is we get a row of zeros. This actually gives us our answer right here. There's not going to be a pivot position in this row because a pivot position must be a non-zero element, and we just don't have that. Now, I'll finish the process anyway, just to try to get this to upper triangular form, because I want to see, that's actually part of a question in my labs, which pivot positions do we have? Like, so how many rows do have a pivot position? Because we don't know until we finish. So because the fourth row does not have any pivot position, it's all zeros, so we do not have a solution. But we can say that 3 of the rows do have one. So although there's not a solution for every possible B, if I do have a B for which there is a solution, there's one free variable. That's this one, x3. So whichever column does not have a pivot position, that's a free variable. So x1, x2, x4, those are our pivot variables. All right. So whenever you have the question, does this system have a solution for all possible right-hand sides? Check if there's a pivot position in every row. So a row of zeros says there's not. All right. So this problem is going to work the same way. Is there a solution? Now, if there is a solution for every B, what we can also say is that the columns of this matrix span the whole space. They span R4. So once again, we perform row operations. All right. So here we have 2/3 times row 1 because that's a ratio. And yes, unfortunately, the number is not working out nicely. Okay. Okay, so we just keep eliminating these entries. This lets me do them all at once. No, it doesn't. Okay. So we're taking care of the first column, and unfortunately the numbers are only getting uglier. But here we still have a ratio of -5 for using row 2 to eliminate this entry in row 3. Okay. And we see there a row of zeros, which we could have spotted up here too, because notice if I take these numbers and multiply them by -5, I get exactly these numbers in the third row. So you can sometimes tell before you actually perform a row operation, oh, these rows, this row is a multiple of this row. For ratios all being the same, -5. That will end up with a row of zeros. So that tells us right off the bat, the columns of this matrix do not span the whole space. So we end up with 3 pivot positions once again, just like in the previous problem. So we don't have a solution for every B. It does not span the whole space. This is another way of asking the same thing. Do these columns span the whole space? Now, for general columns like this, what you would do is you would put these together in a matrix, and you would reduce to echelon form and see if every row has a pivot position. But it turns out we actually don't need to do that here. Because look at, these have an unusual structure that it's not upper triangular like we like to get here. It's an upside down version of that. All right, so I'll go ahead and put them in a matrix so you can see what's going on here. So we put these vectors in a matrix, and then we want to know if this matrix has a pivot position in every row. Okay. So here's what we can do. Instead of performing usual row operations, we can actually interchange rows. So if I were to swap first row and the last, so okay. Let's make a copy of this and do that. Okay. So now, okay. So instead of doing the usual row operations where we take a multiple of one row and add subtract it from another, if we just do a row swap, this is echelon form. And what we can see is that every row does in fact have a pivot position. So yes, the columns of this matrix do span the whole space, R3. So
Hang on.
Yes.
You go back up to number 8. Hang on, stop. You see that? You see V1? That's supposed to be -5 at the end of the verse, not 2.
Okay, hold on. Yes. Oh. I'm not sure what happened here. Almost like I put the transpose in. Okay. All right, just please bear with me and I will fix this right now. Thank you for pointing that out. Okay. All right. Again, my apologies. Every vector is a column of this matrix. All right, now I'll just use these. Okay. Is that straightened out for everybody? Please let me know if not. Wait, let me. So we can see the whole thing. Okay. All right. So as I was saying, since we've had a lot of problems dealing with does a given set of vectors span a certain space, so what we found is that if we have, for example, R4, and we want to know if 4 given vectors, so the columns of a matrix, span R4, it may or may not. But in general, the statement that we can make about having a certain number of vectors span a certain space, if I have, so the dimension of R4 is 4. The dimension of Rn is n, for whatever n may be. So if you have fewer vectors than that, spanning is definitely not going to happen. So what will happen is, like, so suppose I have vectors in R4, but I only have 3 of them. So what will happen in that case is, if I make a matrix like this one, it's going to have 4 rows and only 3 columns. So what will happen in this case is there's absolutely no way to get a pivot position in every row, because the number of pivot positions you can have is bounded by the number of rows you have and also the number of columns you have, whichever is the minimum. That's absolutely the most pivot positions you can have. You might have even fewer than that, depending on the matrix. So if you have not enough vectors for your space, it's not going to span. So you have to have at least 4 vectors to span R4. And as we've seen, even if you do have 4, it might not do it. Because vectors can always be redundant. For example, let's suppose I'm working in R4, and I have 20 vectors. You might think, oh, well, that's definitely going to span R4, isn't it? Well, actually, you can't be sure about that. Because what if 18 of those 20 vectors are linear combinations of the remaining 2? Then you really are only covering a 2-dimensional subspace of R4. Subspaces is something that we'll be dealing with a lot more later. But the point is, whatever the dimension is, you got to have at least that many vectors to span it. That is necessary, but still not sufficient. Okay. This last one is an example of having excess number of vectors. I'm in R4, but I have 5 vectors. So you might think, okay, there's a pretty good chance that it will span. And what will happen is if you go ahead and carry out row operations, in this case, since we've been row operationing quite a bit, I'm going to jump to the punchline here and show you the echelon form. But when I post this in Canvas later, I'll show the rest so that you can see all of the row operations that got us from the original to this. Okay, so what we find here is that, okay, we have pivot positions here in 1-1 position, 2-2, 3-3, nothing in column 4, but we do have a 4th pivot position in row 5. All right. Okay. So every row, at least, does have a pivot position. So we could say answer the affirmative, that these columns do span all of our 4. So if we had row reduced and, for instance, gotten this row to have all zeros, we would only have pivot positions in rows 1, 2, and 3. So then, even though we have, you can think of it, too many vectors, still doesn't span our 4. But in this case, it does. So equivalently, if I had this matrix, so I'm going to label this matrix as A. So what we can say is system AX equals B has a solution for any B in the space R4. Okay. But what also can be said is that the solution X that we would get, because the matrix has 5 columns, is in R5. So this system, AX equals B, whatever B is, will have infinitely many solutions with X4, or that should be a subscript, X4, being a free variable. Why? Because this 4th column here does not have a pivot position. Only every other column does. So what will happen is that for whatever system you have, AX equals B, X5 will be determined by this equation. And then you choose a value, any value for X4, and then you would solve for X1, X2, X3 in terms of X4. Now, do we have questions about any of these or ongoing homework problems? Be sure to unmute yourself if you do. Or maybe just a quiet bunch. One thing I want to make sure that everybody knows about the homework assignments is that I set it up so that you can keep trying the problem. So if you go through the problems and you get them wrong, you are allowed to try again. And the way it would work is after you get it wrong, say you get it wrong, then you maybe move to the next question and get through them all. Then you can go back to that question and you click on the button that says similar question. And if you go ahead and get that right, then you will get credit for it. Also, the way I set it up is if so when the assignment is due, if you do not have 100% at the time, you are allowed to continue working on it past the due date up to 5 days. So what will happen is a late penalty at that point will apply, but only to whatever work you do past the due date. So let's say there's 10 problems, you get 9 right before the due date, so there's 90% that's locked in. And then you go back after the due date and get the last one right. There will be a 25% penalty on that one problem, but since it's only one problem out of 10, you'll still get the full credit. But I want to make sure that everybody knows. I didn't make that explicit earlier. I wasn't sure if my labs would tell you also that you get however many bites at the apple you need with no penalty up until the due date. I saw that on the first homework. Most got 100%. Those who did not, I want to let them know that they could try it again. Ah, yes. Quite a few learning aids that they have here. Since the tests will also be administered in my lab, so what I'm going to do, I've not yet composed the tests, but when I do, I'm going to go through the relevant homework assignments and choose from among the ones that I previously assigned to make up the test. As I mentioned at the beginning of the semester, because of various COVID-induced considerations, tests are not proctored, although there will be a time limit. But I'm glad that feature is helping. Yes, so everything is in my labs. So really, you can almost think of a test as being another my labs assignment. All 3 tests. It's the 2 during the semester and the final exam. So really, the only difference is the fact that it's timed. And well, the way I'll do this is the tests the test will be each test will be password protected. But what I will do shortly before the test is released, I will announce to you all in Canvas what the password is. The reason for the password protection is that because it's a timed test, once you start the test, the clock starts, and it will not stop for any reason. So it'd be a shame if you accidentally entered the test when you weren't really planning to take it at that time, and then your clock runs out. So the password will be used to protect you from doing that. But yeah, other than that, it'll have a look and feel of pretty much of a MyLabs assignment. When I make the test, I will make a duplicate of it, and that'll be made available to you all. That will be a practice test. So that way there won't be surprises as to the what the test will entail. Last call for any questions. Also, I've seen this in my other classes too. When I adjourn class, so when I tell everybody that it's over, naturally people start leaving very quickly. But then there's always a few who seem to be zombie students who are just kind of lingering there. And then I ask them if they have questions, and they don't. So if you're here at all, please pay attention for when things end too. It should be tuned in enough to at least know that. So this is just something that I've noticed since doing these classes in teams. Okay, so what I will do is end the recording right here. If you want to ask questions on a more individual basis, I will stick around. Let me get this stopped.